I previously built a motorized roller blind project and it reached nearly 300,000 views. After reading your feedback, I decided to refine the design and improve the overall installation experience. In the original version, mounting the motor and the electronics required drilling holes into the metal profile and the wall. To eliminate this, I redesigned the system to be fully modular and drill-free. The electronics enclosure is now integrated directly into the motor mounting bracket using a sliding connection, making installation faster and cleaner. The bracket itself was also redesigned to fit perfectly into standard roller blind mounting profiles without modifying the metal frame. Internally, the drive gear and bearing system were strengthened to reduce motor load and improve long-term reliability with support for different roller tube types. On the electronic side, the PCB was made smaller and an ESP32 was added for Wi-Fi and Bluetooth connectivity. The system now calibrates and remembers its end positions, allowing smooth and automatic open and close operations. If you're interested in these improvements, let's start by 3D printing the parts and move on to the assembly. With the motorized gear mechanism fully assembled, it's time to move on to the electronics. I aim to keep the circuit simple, compact, and functional, and designed the PCB to be as small and efficient as possible. As usual, I headed over to PCBWay, opened the PCB order page, uploaded the Gerber files, and completed the order for 5 PCBs for just $5. PCBWay also offers PCB assembly and 3D printing services, so if you're looking for a more professional assembly or high-quality 3D prints, they're a great option. Many thanks to PCBWay for supporting this project. At this stage, we can move on to soldering the components. You can find the full component list and a link to the project page with detailed information in the video description. To make SMT assembly easier, you can order a stencil along with the PCB and use it to apply solder paste. Alternatively, you can carefully tin the pads using a soldering iron, place the components, and then reflow them in an oven. Now that the board assembly is complete, it's time for programming. I chose the ESP32-S3 for this project because of its compact size and support for both Wi-Fi and Bluetooth. You can find the full source code and all project details through the link in the video description. In short, the firmware uses the Blynk Cloud infrastructure, with Wi-Fi selected as the communication method. Once the code is uploaded, we can mount the PCB onto the motor gear assembly and complete the wiring. After connecting the motor connector, I use a 5-volt 3-amp power supply. Please make sure to double check the polarity before powering it up. Now, a quick note about the board. Some ESP32-S3 Super Mini boards can suffer from low Wi-Fi antenna performance, and since the PCB will be placed inside a closed enclosure, this can become an issue. To avoid that, a small modification is needed before mounting the board. By soldering a short piece of copper wire to one side of the Wi-Fi antenna pad, we can significantly improve signal strength. In my workshop, I had an old adhesive Wi-Fi antenna from a development board. I cut the cable and soldered it directly to the antenna pad, which helps boost Wi-Fi reliability. After that, the ESP32 is installed onto the PCB. The antenna is routed outside the enclosure, and the enclosure is mounted to the back of the motor gear assembly. Finally, it's time to install the motor gear onto the roller blind. I remove the original mounting parts from the blind profile and tube, then install my custom motor gear set. To control the motorized roller blind, I open the Blynk Cloud mobile app. You can find detailed instructions on how to set up the app on the project page linked in the description. Now let's test the application. First, move the roller blind to the starting position, then press the Calibrate button once. This resets the current position and sets it as 0. Next, activate the down blind button. The motor gear will start moving and the blind will begin to roll down. Wait until the blind reaches the desired position. Once it does, press the down blind button again to stop the movement. As you can see on the app screen, the number of steps is now saved in memory. From this point on, when you press the up blind button, the blind will automatically return to the starting position, moving by percentage based on the stored step count. When you activate the down blind button again, the blind moves back toward the end position, once again stopping precisely at the calibrated point. If you ever want to reset the start and end positions, simply press the Calibrate button again and repeat the process. The app and the motor gear work very reliably during short movement tests. Now let's see how the system performs over a longer travel distance. To do that, I mounted the roller blind in front of a window and started a real-world test. First, I opened the blind to the position where I want it to start. While the blind was in this position, I pressed the Calibrate button once. Then, using the down blind button, I started the motor gear and let the blind move all the way to the fully open position, where the window is completely covered. Once the blind reached the desired open position, I released the down blind button. As a result, the total number of steps was saved and displayed in the app. By activating the up blind button, the blind closes automatically based on the stored percentage, allowing the window to open again. As you can see, the blind reaches the 0 position and stops automatically. If you like this project and want to see more content like this, don't forget to subscribe and leave a like. Thanks for watching.